Now, today we are going to discuss the next lecture of tree. In the previous day class, we discussed definition of tree and definition of binary tree, their properties. Now we'll discuss spanning tree. Spanning tree definition. A tree T is called a spanning tree of a connected graph G if T is a subgraph of G and T contains all vertices of G. For instance, the subgraph in red line in the figure is spanning tree of the graph shown below. This is the spanning tree. Which is the spanning tree here? This part, this part, this part, this part, this part, and this part. This is the spanning tree. And the complement, that blue line of the spanning tree in a connected graph G is called cotree or tree. It is denoted by T bar. The cotree is drawn with blue lines. The spanning tree is the largest tree with maximum number of edges among all the trees in G. The complete graph Kn has n to the power n minus 1 different spanning trees. The edges B1, B2, B6 are branches of the spanning tree, while the edges C1, C2 up to C are the chords shown below. The branch of tree is nothing but an edge of the spanning tree chord. An edge of G which is not in given spanning tree is called chord. An edge which is a branch of one spanning tree may be a chord of another spanning tree. Definition, we have to remember it. Let T be a spanning tree of a connected graph G. G has n vertices, E edges, then T has n minus 1 branches and E minus n plus 1 chords. Next, find all the spanning tree of the graph given below. This is the graph. How many vertices are there in this graph? There are 3 vertices. How many edges? A, B, C, D, E, 5 edges. So this graph has 4 vertices. This graph has 4 vertices. Hence, each spanning tree must have how many edges? N minus 1. That means 4 minus 1, 3 edges. Thus, each tree can be obtained by deleting 2 of the 5 edges of G. This can be done in 5C3 ways, that means 10 ways. Except the 2 of the ways lead to disconnected graph. Thus, there are 8 spanning trees shown below. 1, 2, 3, 4, 5, 6, 7, 8. All the spanning trees, all are connected. Subgraph of this given graph contains no circuit but contains all vertices. This is the spanning tree. Find all the spanning tree of the graph G. So this is our graph G. From this graph we have to find out all the spanning tree. So the graph G has 8 vertices and hence each spanning tree must have 8 minus 1, that means 7 edges. Thus, each tree can be obtained by deleting 2 of the 5 edges of G, 2 of the 7 edges of G. That means this can be done in 5C3 ways. Except that 2 of the ways lead to disconnected graph. Thus, there are 8 spanning trees shown below. First we remove all loops and parallel edges. This is the loop at the vertex P and parallel edge in between D. We delete it and we are getting this graph. Next we are deleting these 2 edges. We are deleting this edge and this edge. We are getting this is the spanning tree. Next we are deleting this edge and this edge. We are getting this spanning tree. Next we are deleting this edge and this edge, we are getting this spanning tree. We are deleting this edge and this edge, we are getting this spanning tree. Here we are deleting these two edges. Then we are deleting these two edges, we are getting this spanning tree. Deleting these two edges, we are getting this spanning tree, and we are deleting these two edges, we are getting this spanning tree. So here we are getting 8 spanning tree from this graph. Find all the spanning tree of the following graph. Here is another one question. Find all the spanning tree of the following graph. So this is our graph G. We can find spanning tree. Step 1, delete all the loops and parallel edges. So this is the loop, we are deleting it. There is a parallel edge. First we are deleting it. This is the step 1. In the next step, first we consider what is the circuit. From the circuit we delete one edge and we are making our graph circuit free. So here we are deleting, suppose this edge. We are considering A, B, C, A, and we are deleting the edge AC. Okay, so this portion is circuit free. Now we are choosing this is D, B, E, D. Now we are deleting any edge from this circuit. Suppose we are deleting this edge and rest portion is circuit free. Next we are deleting D, E, G, D. This is one circuit, and from this circuit we delete any edge. Suppose we are deleting this edge. Okay. Next. Next. So this portion is circuit free. Now we are considering this circuit. This we are G, E, F, G. We are deleting any edge from the circuit. Suppose we are deleting this edge. Now we have this one. Next, B, E, F, B. This is one circuit. We are deleting any edge from this circuit. Suppose we are deleting this edge from the circuit. Next, again B, C, F, E, there is a circuit. So from this circuit we will delete any edge. Suppose we are deleting this edge. So we are getting one graph. This is circuit free. And this is a spanning tree. Spanning tree is a subgraph of a connected graph, contains all vertices of G. So this is our required spanning tree. Now there is a theorem: if G has a spanning tree, if and only if G is connected. So let G be a connected graph. If G has no cycle, then it is shown spanning tree. But if G contains a cycle, then delete an edge from the cycle. According to a previous theorem, the graph is still connected. If this graph has no cycle, then it becomes a spanning tree of G. Otherwise, repeat the operation till an edge from the last cycle is removed, given a connected graph without any cycle. This left out graph contains all vertices of G. Because no vertices were removed in the above deletion process, so this left out tree in a spanning tree of G. Thus, G has a spanning tree. Conversely, let G be a graph having a spanning tree, say T. Let V1 and V2 be two arbitrary vertices of G. Since G contains all vertices of G, therefore V1 and V2 belongs to T. Since T is a tree, so T is connected and V1, V2 are connected by a path. So G is connected. Fundamental circuit. A circuit formed by adding a chord to a spanning tree of a graph G is called a fundamental circuit of the graph with respect to the spanning tree. In figure A is a spanning tree of the graph in the figure B. In figure C, the circuit ABCA is forming by adding an edge AC to the spanning tree in the figure A. This circuit is called a fundamental circuit of the graph shown in figure B with respect to figure A. Similarly, BCDB is another fundamental circuit obtained by adding the chord BD to the spanning tree A. So this is the process. How will you find the spanning tree? Actually, which edges we are deleting from a connected graph of getting spanning tree? That edges, if we are adding that edges to the last spanning tree one by one, we are getting fundamental circuit. There is a note. Let T be a spanning tree in a connected graph G. G has n vertices and E edges. Then there exists E minus n plus 1 number of fundamental circuits formed by T. Find fundamental circuits for the graph G. This is our graph G. First, what we are doing, we are deleting loops and parallel edges. There is a loop, we are deleting it. Between these two, there are parallel edges, we are deleting these parallel edges. Then we redraw our graph. In the next step, we are considering BCDB. We are considering BCDB, this circuit, and we are deleting the edge BC from the circuit. That BC we are deleting. Then we are getting BDC, this portion. And here we are considering the circuit CDEC, CDEC, and we are deleting that CE, and we are getting this portion. Next, we are considering BDGB, BDGB, this circuit, and we are deleting the edge DE. Then we are getting this portion. BD. We are deleting BD. Next, we are considering circuit DGCD. DGED. We are considering this circuit and we are deleting edge DE. Then we are getting this. Next, we have this circuit GEFG. We can delete any edge. EFGE. Then deleting the edge EF. We are getting this circuit. This is the spanning tree. And our connected simple graph G has 11 edges in vertices. So how many fundamental circuits are there? By definition, we know that E minus n plus 1, that means 5 fundamental circuits are present. And we are adding this. Suppose we are adding EF. Then our circuit is GFEG. This one. Next, if we are adding our next circuit, that means first chord BC. If we are adding our first chord BC, what we have? B, C, D, G, B. B, C, D, G, B. That is our first circuit. Next, delete this one. Again, we consider our next chord CE. Our next chord is CE. Then we are adding this CE. What we have? C, D, G, E, C. C, D, G, E, C. That is our fundamental circuit. Next, we delete this one. After that, our next chord is BD. Now we are adding BD. What we have? Then our next fundamental circuit is B, G, D, B. B, D, G, B. That is the fundamental circuit. Next chord is DE. If we add, first delete this one. Don't add all the chords at a time. Then our next is DE. Then our fundamental circuit is DGED. DGED. That is our fundamental circuit here. Then our next chord is CE. If we are adding CE, what's happened? Which one I asked? So we can choose this one as our edge, but for this reason, many times I told you that you have to delete all the chords from the spanning tree, just add only one chord for which we need that fundamental circuit. So here we are adding C, E, and our fundamental circuit is C, D, G, E, C. So this is our fundamental circuit. The given graph next definition. The given graph may have more spanning tree and so more corresponding fundamental circuits also. Rank and nullity. The number of branches in a spanning tree of a graph is called its rank. The number of chords is called nullity of the graph G. The nullity of a graph is also called its cyclomatic number or first beating number. If n is the number of vertices, e is the number of edges, and k is the number of components in a graph, G, then rank R equals to n minus k and nullity mu equals to e minus n plus k. This implies that rank plus nullity number of edges in G. If G be a connected graph, then rank n minus 1 and nullity e minus n plus 1. So this is the uh, lecture of spanning tree. Up to this, so we can recall what we have done. This first we are trying to uh, understand the definition of spanning tree. Next, branches and chords. Then there is a remembrance. We have to remember it. Then we are trying to find out all spanning tree from this graph and all spanning tree from, again we are trying to find out all spanning tree of this graph, again spanning tree of this graph. Then there is a theorem, G graph G has a spanning tree if and only if it is connected. We are proving both the cases. Then we try to understand the definition of fundamental circuit. Then there is a note, find fundamental circuit of the graph G. We are trying to consider the circuit, fundamental circuits. We are trying it. Then there are some definitions of rank and nullity. Then up to this. So we can stop here. We will discuss in the next class.